You pick 6 people. Okay, so any 6 people. 6 people in this classroom, 6 people on campus. You go to the beach, people are hanging out by somewhere. Pick any 6 students, or go out to the streets of Philly, pick 6 anywhere in the world. Okay, so here are 6 people. Okay, and here's the claim I'm about to make, that you will always find among these 3 people 3 mutual friends, or 3 mutual strangers, one of the 2 or both. Now, what I mean by mutual friends, first of all, let's agree on some terminology here. Maybe we should go with this slide here. What do we call friends? Okay, we have to agree on some terms. So use the loose sense of the word. 2 people, they've met, they're friends. Just like on Facebook, you may have some people you've never met, friends, you call them friend, Facebook friend. Okay, so you met, 2 people have met, they're friends. People have never seen each other, don't know about each other's existence. They are strangers. So let's agree that any 2 persons that you can pick in the entire world, they have either met or have not met. Now, what do I mean by mutual friends? What does that mean? 3 people are mutual friends. Okay, so let's call that a club, I guess, another piece of terminology, or a clique, it's sometimes called. Here are 3 dudes, okay, and let's draw a connection between the 2 if they have met, and not draw a connection between the 2 if they have not met. Okay, and notice that what we're doing already. So I haven't even understood the problem. Maybe some of you already have, maybe I haven't yet, but I'm already doodling. That's the most powerful mathematical tool of all time. Doodling, right? You sit down and try to make sense of the problem, okay? People all of a sudden are represented by dots. Knowing or not knowing each other is that relation is represented by drawing a line or the absence of a line, not drawing a line, right? What do I mean by relation? If you've taken like 1166, and I don't mean to confound the issue any more than it needs to be by referring to some terminology. The point of the terminology is to facilitate communication rather than to obfuscate it. But if you remember, what is a relation? So when I'm saying connection, I represented it with a connection here, right? Any other comments? If you maybe in a math course you've talked about relations, specifically relation, you gave a definition maybe, and we don't need that definition, but whatever you remember of what a relation. So maybe you have talked about symmetric relations, non-symmetric relations. People remember?
It's kind of a more abstract notion of a function.
Oh, okay. So, okay, what do you mean by this?
I guess what I mean is that a function is a type of relation.
You're correct, but so here's what is a symmetric relation? So when I say 2 people are friends, they met each other. Is that a symmetric relation? What is meant by symmetric relations? Yes, please.
Go ahead.
Yeah, please.
So a symmetric relation would be a relation in which A is connected to B and B is also connected to A, both in the same way.
Right. So being friends on Facebook, right, is a symmetric relation. If A is friends with B, B is friends with A, there's no way for A to be friends with B and B not be friends with it. Does not work in real life, right? So what's a non-symmetric relation? Doesn't always. So what's an example of a non-symmetric one? I don't know. Follows on Twitter is not a symmetric relation. Being in love with is not unfortunately, as life would have it, is not a symmetric relation. You may be in love with somebody, that somebody may not be in love with you, or you may think you're in love, they may think you're in love, whatever, right? So not all relations are symmetric, but friendship here in the context of Facebook, at least, is a symmetric relation, right? That's the reason I'm drawing this. So later we'll have this terminology for these things. So later we'll have these structures like this, we'll call them graphs. These guys, the lines that I'm drawing later, we'll call them edges. Okay, so these dots that we call dots, later maybe we'll call them vertices, and we'll call them, I don't know, nodes or vertices. These lines will be called edges or arcs. That's all fluff, trust me. What matters is the representation of the problem. The fancy terminology as it goes is you're modeling the problem using graph theory. That's the term of what we're doing, really. We're doodling, and that's the powerful tool. We're representing people with dots. We're drawing some lines with the hope of gaining some insight into the problem. That is the initial phase of, call it problem solving, if you will, of gaining some insight into the problem. That's what we're trying to do, because I don't yet understand the problem. I gave it to you. I'm not quite grokking it yet. So, but are we clear on the terminology so far, at least? So what we mean by friends, what we mean by strangers, a particular way of drawing this, and let's see if this is even going to be helpful in gaining any insight to it. So we have these 6 dots representing people. Now, can I ask you a couple of things? Scratch paper here, good. First of all, how many, if I have 6 people, how many connections, what's the maximum number of connections that I can have between 6 people? That needs further clarification. First, let me ask you how you understand this. So suppose I have, like, I don't know, let's start with 4 people. 1, 2, when I have 3 people, what's the maximum number of connections? What do I mean by this? How many pairs I can select, where pairs are distinct elements selected from a set of 3 objects. Objects are now people, and I'm selecting pairs of people. You may, this terminology that I'm using now, reframing the problem slightly differently, I'm using different words. That terminology may be familiar to you from some probability course, maybe. I'm talking now about objects being in a bag, and I'm picking 2 at a time. Number of ways of selecting pairs from a bag of n elements, something. Now it's a different terminology. The first attempt at doodling was to draw 3 dots and draw all possible lines between any pairs of dots. Am I really talking about the same thing? Yeah, people help me out.
Wait, I have a question.
Sure, please.
So is A to B and B to A 2 separate connections, or is that one connection?
That's one connection. So when I draw a line like this, right? That's A and B. That's it. They know each other. A knows B, B knows A. We're assuming that it's a symmetric connection. Yeah, good point.
Okay.
So it's not like following on Twitter, like A follows B on Twitter and B is not in love with A. Not that kind of thing. They're friends.
So will there be 3 connections here?
Yeah, so we have 3 possible, the maximum number of connections is 3, right? So we have A, B, C, and we have 3 connections. Question, what if I had 4 people? A, B, C, D now, or 1, 2, 3, 4. How many connections do I have maximum?
It'd be 6, right?
There will be 6 connections, okay? So how about if I had 5 people? Okay, getting maybe repetitive, but how many connections? So you know what's coming, right? The mathematician is the person who cannot resist the inclination or an urge to generalize. Yes, I know that I have 3 possible pairs in a set of 3 elements, but the next natural to a mathematician question is, what if I had n people? What's the number of connections, maximum number of connections that I can have? And by now, he knows a way of rephrasing this question is, if I have a bag of n objects, how many different ways can I select pairs? Did somebody have a hand up, please?
Oh yeah. Would that be n choose 2?
Yeah, that's right. So n choose 2 is just notation for what we just described, right? And some of you may remember the formula that was n factorial, n minus 2 factorial, 2 factorial, which simplifies to n times n minus 1 over 2. But suppose not everyone knows this, so I'm not expecting people know this, right? So yes, that n choose 2 was that, right? Is that what you meant?
Yeah.
Yeah. So yes, so if I had n people, so for example, when n is 5, here I drew like 5 persons. So what am I saying? So what you've just suggested, n choose 2, is in our way of representing this setup, is the number of connections I can draw on the set of 5 elements. It will be, if you plug n5 into this formula, you get 10. The 10 connections I can draw like this, right? There are 10 connections. And if you had 6, you would have 15 connections, and so on. Okay, just simply that. But for a second, can I say I have no idea what this formula, actually, let's leave this on the side. And if you don't remember this, just forget it's here for now. Let's account for this number of connections slightly differently. Can I ask you this? If I have a structure like this, 1, 2, 3, 4, 5. Okay, so here's 6. And I want to insert another page. That's this. Okay, that's good. Okay, so now I have 6 people. 1, 2, 3, 4, 5, 6. How do I account for all possible connections here? So 1 is connected to how many people?
5 different people.
connected to 5 different people, right? Connected to 5 different people. So I've just accounted for 5 connections. So I want to count for all of them. Now I go to number 2. How many 2 is connected to 5 people, right? Also, 3 is connected to 5 and so on. But when I get to number 2, I really need to account only 4 new connections, right? Because 1 to 2 is already connected. So I have like 4 new connections that I have to add when I'm counting methodically like this, as I'm suggesting now, the number of possible connections. Then I count all the connections from 1, then I count all the new connections from 2, then I count all the new connections from 3. Let's go with 3 for a second here. From 3, how many people is 3 connected to? Well, 3 is connected to all 5 of them, but I've already accounted for these 2 connections, to 2 and 1. So the new connections are to 4, 5, and 6. These are 3 new connections. 3 connected to 3 new, and so on. Does that make sense? Right? So, and then I go like 4 is connected to 2 new, 5 is connected to 1 new. When I get down to 6, there's no new connections to account for. So right now in this picture, I've drawn all possible connections between 6 elements. Later, this kind of structure will have a name. We'll call it a complete graph on 6 elements. But for right now, I'd like you to forget even that I've even mentioned this name. This graph, this structure will have a name. We'll call it K6. But that's later. For now, these are people and possible connections. This is the total number. So the total number of connections, which you've suggested a second ago was going to be this number, which I don't yet know what this is. I'm going to count this number slightly differently, because what we just discovered with your help is that the number of connections that I have is 1 plus 2 plus 3 plus 4 plus 5. So on 6 people, on 6 people, that's how many. So if you count that better be 15. I mustn't make mistakes. So that number, how do you count this for any n? So n minus 1 would be the number of connections for n people. If n equals 6, then this is the number that I want to compute. Do people remember what this has a name, and it's not important to know this name, but do people remember what's this when you have a sequence 1, 2, 3, 4, 5, 6, 7, 8, 9? What is the name of that sequence? There may be something on the chat I'm missing, so please let me know. I definitely missed something here and there.
Would it be an arithmetic sequence?
Yeah, that's exactly what it's called. It's called the arithmetic progression, right? What's the sum of it? Well, one option is to Google it, but why Google it? Here's a neater way. So this is the sum that I want to figure out what that sum is. I don't know what that sum is, but I call it X or sum, variable name. That sum, I'm going to write out a little bit differently. So this is the sum that I'm computing, plus 3 plus 2 plus 1. What is this sum, this 2 times sum? You see that this sum is 6? This sum is 6. You see that they sum to 6. They sum to 6. Everybody sums to 6. Do people see that? Or am I having an optical illusion? How many 6s do I have?
5.
5 times 6s. 5 6s. And that is 2 times the sum. So what is the sum then?
15.
Yes, it's half of that. Exactly. The sum is 15. So if I'm summing 1 through 1 plus 2 through n minus 1, that's going to be n times n minus 1 over 2, right? The sum of the first n terms. Isn't that exactly what you suggested 2 seconds ago here? This is why n choose 2, we actually just proved that n choose 2 is that number. N choose 2 is that number, because we described n choose 2 in 2 completely different ways. Okay, so now back to the problem. Okay, so we've fallen into a bit of a trap that every mathematician falls into. You start thinking about some problem, something comes up, and you go off on a tangent, and you may spend a lifetime without attaining any results thinking about a problem that tangentially came up. But here, fortunately, we can manage our lives a bit more predictably. Can somebody say?
So
yes, please. Yeah, please.
I was going to say that the question is basically asking there is at least 3 people that know each other or they don't know each other. So it's black or white, 1 or 0.
Exactly. So that's exactly right. So thank you. So in this new kind of small language that we've just developed here, what I'm asking then, we've just managed to reframe the question in the following way. Given 6 dots and given the connections between the dots, given all possible connections between the dots here, where each one of those connections may be one of 2 kinds, either red or blue. Can we agree? Let's introduce some terminology. Red connection, know each other. So these gray connections that I was drawing here, those are possible connections. So the gray represents either blue or red. So blue connection, blue. Does that make sense, what I'm saying right now to people? I'll clarify this in connection. Okay, so later we'll call these connections edges or arcs. Okay, don't know each other. Okay, so from each point then, I have an either red connection emanating or a blue connection emanating, no matter which point you take in this graph. So gray connections, again, gray connections are all possible connections. Actually, let's draw them. So gray connections, I don't know what they are. Okay, so these are gray guys. Okay, so these are all the 15 possible connections that I have. Now, each connection is between some 2 people. And those people either have met or they have not met. There's just logically no other possibility. So each connection is either red or blue.
Well, what about the possibility that 2 of them know each other?
Yeah, 2 of, okay, so what we're saying is 2 people, right? So each connection, isn't each connection between 2 persons?
Well, we're talking about 3 people. So if we say that.
Oh, okay. So before we get to 3 people, good point. So we'll be discussing this right now. What I've done so far, I've configured 6 people somehow. I've thrown them onto the plane, right? Those 6 people, every pair of the 6 is somehow connected. Agreed? People agree?
Yeah.
Every pair is somehow connected. Now that connection between any pair of people, any 2 people, can be either red, signifying they know each other, or it can be blue. They don't know each other, the pair. So each of the possible, yes, please. Somebody, did somebody
Oh, no, sorry, I was just agreeing.
Yeah, oh, okay. So are we on the same page, everyone?
Yeah.
Okay, so each connection is either red or blue. So the question becomes, we're looking for triangles of the same color. Does that make sense? So now we're back to the question that you probably had in mind when you raised this issue, is that the problem itself is asking, pick any 3 persons here, then you're guaranteed to find either a blue triangle or a red triangle, right? Do people now see? Let me write this down. So this is equivalent in a graph like this, in a structure like this. I guess we can call it a graph. I mean, it's not just another word. In a graph like this, graph like this. And we mean by like this. What did I mean by like this? By like this, I mean graph on 6 points where each connection is either red or blue. In a graph, and let me be more specific here. In a graph on 6 people, later we'll call them vertices, but here, let me call people, right? 6 people, where each connection, and later we'll call connections edges, where each connection is either red, well, let's do either red or blue. So every possible edge of the 15 is either red or blue. You will always find, always find either a red triangle, or a blue triangle. You see that I've reframed the problem in a different language. this, and this are the same problem. Before we move on, we have to agree on this, that this and that are the same blue triangle. This is 4. People agree?
Yes.
Okay, so now this is something that we can justify. And now I'm going to need your help in justifying this. Any thoughts? So notice here, let's observe a couple of things, even if you have thoughts. Sorry, I'm interrupting you. First of all, notice that we're claiming 6 people. Later, I will be asking you something like, why do they have to make 6 people? Why doesn't it work for 5 people? And so on. But those questions are coming later. And sorry, I guess I interrupted you because I posed the question, well, how do we go about this? Maybe some people have an idea and I've just interrupted the flow. So what are the ideas?
I was going to mention, or going to rather ask, can we choose to prove that it isn't true? Because, I mean, there's, if 1 knows 2 and 2 knows 3 and you're going around in a circle, you're never going to have a group of 3 people who all know each other or all don't know each other.
Okay. So let's actually pursue this for a second and let's see where it gets us. So can we do some scratch work here on the side for a second? So what was the suggestion again? So we have 6 people, right? So did you suggest a circle or something?
Yeah, 1 knows 2, 2 knows 3, 3 knows 4, 4 knows 5, 5 knows 6, and 6 knows 1.
Okay. But, okay, so can we make, so they know each other. So these are red connections, right? In this new nomenclature that we just introduced, new terminology, rather new notation, let's say red standing for know each other. But you see that the other gray connections, for example, here, do you see that I have strangers?
I see.
You see?
Yeah.
So we're guaranteed to, so good, excellent point. Why? That's how you proceed when you're trying to make sense of it. Yeah, that's exactly the way to do it. So what if you questioned it? This is excellent. So you question, is this really true? And that's exactly what you should do. You come up with a counter, try to come up with a counter example. Or if you don't, then you'll end up what you in 1166 maybe called proof by contradiction. Notice that, yeah, so I'm trying to, that's exactly what we want to prove. So no matter what configuration I have, maybe I didn't go around the circle. Maybe you could have suggested some other possible connections. Maybe these guys also knew each other and so on. I'm still, now I'm guaranteed there. I didn't find red triangle. Here I even have like, I still don't have a red triangle here, but if I drew maybe like, I don't know what else here. So here I have both a red triangle and a blue triangle. But it's possible that I have a blue triangle, but not the red one, or the red and not the blue. So that's exactly what we're trying to prove. So no matter how I color these edges, I'm guaranteed to have either a blue triangle or a red one.
I guess I have an idea.
Yes, please.
Can we draw, I guess the first, I want to say red would be 1, 3, and 5, and then blue would be 2, 4, 6.
1, okay, so 1, 2, let me try. That's what you're suggesting here.
So pretty much, yeah, red on even, blue on odd.
Okay, so red on even and blue on odd. Yeah, it's a possible configuration. Okay, and
so if we were to complete the triangle from 1 to 3 to 5, so 3 to 5 as well. So I guess you'd have like almost like a like a Star of David kind of deal where
okay,
the triangles would overlap.
Let me see. So we have 6 elements here. So to draw that star.
So
yes,
yeah, you see the one is connected with the red. Disassociate the one with the red. So 2, 4, 6, not 1, 2, 4, 6.
2 to 6, and not 1 to 6.
Right, because like I guess so just make a triangle between 2, 4, 6.
Sure. Can I ask you, like, yes,
yeah,
we can draw this, but what are we doing? Like, what are we drawing towards, if I can ask you?
I guess in this situation we'd have 3 mutual and then 3 non-mutual.
Yeah, but we are given, so excellent point, because what we're doing here is we're coming up with yet another example where we'll have such triangles, right? Am I correct?
Right, and I feel like it'll satisfy the the question. I don't know if I'm missing anything.
It will, yeah, no, you're not missing anything, because whether it's this example or any example you may have come up with, right? It will be there. That's what we're trying to prove. You're coming up with yet another example where you will have a green triangle and the red triangle. But the way your mind took you at this very moment is let me give yet another example where I will have the red triangle and the blue triangle. Am I correct or no?
Mm.
Am I correct?
Yeah.
So what we want to show is that that will be the case even if I didn't attempt to come up with a pattern. The mind is a strange device. We look for patterns. It's important now to also employ logic so that we don't look for those patterns that we know exist already. Unless we want to contemplate those patterns, there would be another legitimate reason to think of them. But for now, we want to prove that no matter how we configure, how we color these gray edges here, no matter how they're colored, there will always be a red triangle and always be a blue triangle. That's what we want to like convince another person of this. Does that make sense?
Yes, it does. Is there a configuration where it won't make sense between three? Like, three mutual, three non-mutual? Is there like a counter to this?
That's what we want to prove that it does not exist. That's our goal.
Okay, so we're just going to exhaust.
To find it.
So we're just trying to exhaust all the possibilities where this would be true.
Now, that's a good point. Can you hold that thought? When you use the terminology exhaust all possibilities, that already suggests a different solution. Can you hold that thought, and we'll come back to that in like 15 minutes?
Yeah, that's fine. Anybody
else was going to mention something? I may see some hands raised. Please say something, because I don't have all of you at the same time.
Yeah, so there was the idea is that we want to try to generalize and say, okay, why does this always occur? You could give, I'm not sure how many different possible combinations of connections, like how many different diagrams you can draw.
Okay, I'm sorry to interrupt, but actually you are sure, and I will be asking you this question and you will be able to answer that question, but sorry I interrupted you.
You're right. I'm just me right now in this moment. I didn't think to think about it, but the point is that it is a finite number, and so you could, in theory, just illustrate every single possible combination and say in all of these there's a triangle, but that's tedious. And so I think the objective I think is to use what we know to prove that there will always be a triangle. Based on the relationships in the model we've constructed.
Yes. So you sort of gave more detail to the same point that we were making a little bit. Can we hold on to those ideas for a second, for like 15 minutes? Because I do want to discuss that, because that's yet another solution. And maybe now you're giving me ideas of what exactly to put in your homework, because your homework isn't ready yet. So going back to this, now is it clear? So we kind of discussed, so if anyone can make a couple of more comments will be great, but now I actually want to carry out this may involve some logic, but that's okay, you will like it. So I'm going to try to convince you of this, and your job is to be as skeptical as possible and catch me if you find a flaw somewhere, or ask me if something is unclear. Does that make sense? So I'm going to try to prove this to you now. So here I'm going to argue in the following way. Well, I have these 6 people. Okay, so I'm going to be proving this equivalent proposition here. I have this 6 people, right? So without loss of generality, kind of like maybe strange term for me, but what this means is pick any one person, anyone that makes you happy. Suppose this guy, call this number 1. I could have picked this guy and called him number 1, it doesn't matter. So I have 6 people, pick one guy. Here's one guy, could be that guy, I don't know, doesn't matter. Okay, so let's not label these. So this one guy is connected to 5 other people somehow, right? Either he knows some of these 5 people and doesn't know 5 other people. So observation 1, bullet point 1, of the 5 people connected to this guy 1, can we call this like Bob or something? Bob instead of 1, connected to Bob. Okay, the other 5 people are these guys. Of the 5 people connected to Bob, we must have, and this is what you should question, either 3 red connections or, okay, that was wrong, must have either at least 3 red connections. So these are all possible connections emanating from Bob connections, or at least 3 blue connections. Now we want to make sure that this makes sense to all of us. Why should that be the case? What is it them claiming? Okay, so if you'd like this, okay, so to some people, this may make sense, and you may say, okay, I feel it in my gut, it's true. That's not going to cut it. You may, I'm not questioning that you may not, but let's explain exactly what's happening here. I think the easiest, and maybe I may be wrong, you tell me, the easiest way to think this is maybe think about the complement of the claim that I just made. I just told you gave you some logical proposition, which is like ORed proposition. And so please forgive me if you think I'm complicating this, but let's see if I can follow this. I'm not complicating this at all. So I have 2 propositions. So one is like P, and then the other is like Q maybe. Okay, so P stands at least 3 are red. And Q stands for at least 3 emanating, so these are the gray guys emanating from Bob. So these gray guys emanating from Bob, 5 of them, it must be the case, there's no other way, that I either have at least 3 red or 3 blue. Now, please help everyone understand why that's the case. When would this be not true? Would not be true, let's say this way, would not be true if, what does it mean to say that it's not the case that I don't have either at least 3 red connections or 3 blue connections? Would not be true. Okay, so if you want the hint, it's going to be like not, I'm going to say not Q and not P, and I'm going to say and. Actually, let me write the word and. That I've just negated the first. I'm going to write and like this. And here, just not to confuse people, I'm going to write or. So this above, I just rewrote the above in shorthand here. This guy here says, at least 3 connections are red. That's P. This guy says at least 3 are blue. That's Q. So my claim is that it is always the case that P or Q is true every time. There's no universe where P or Q is not true. Because if P or Q were not true, and we're going back to an earlier suggestion, how about let's try it by contradiction, one of you suggest. If P or Q were not true, then what would be true? That I would have at most like fewer, okay, so let me just, fewer than, so this is not P. There's going to be fewer than 2 red connections and fewer, this is not Q, fewer than 2 blues, right? People agree?
Yes.
Yeah, this is a proof by contradiction, right?
Yeah, yes. So we haven't done any proof yet. We've just simply negate. But your point is well taken.
And
so yes, please.
Then there's nothing left for the last connection.
Exactly.
Because there's only red and blue connections.
Yes, exactly. The point I'm trying to make. So you have 5 these gray guys here coming out from Bob here, emanating from Bob. You have 5 possible connections. Each one of those 5 can be either red or blue. If fewer than 2 of them, fewer than 3, I should say here. Okay, now I made a logical mistake here. Fewer than 3. Okay, so 2 or less. So P says 3 or more are red. Here I'm saying not P is up to 3 can be red. That's it. You can't have 3 reds. You can have at most like 2 reds and 2 blues. Then you just simply don't have 5 total connections because every connection is either red or blue, right? Agreed? Are we on the same page here? Let's make sure that we're on the same page. So from Bob, I definitely have either 3 reds or 3 blues. So got either 3 reds or 3 blues, or 3 blues. You may have more 3 red, all of them can be reds, but it's definitely the case that I have like either 3 reds, maybe these 3 reds here. How about these guys? And Bob is connected to A, B, and C with red ones. I definitely have either that, or I have Bob connected to like some 3 blues and the others are reds somehow. But let's leave this aside. Let's concentrate on this picture. I have something like this. Bob is connected. Bob has 3 red ones, case number 1. Case number 2 is Bob has at least 3 blue ones. Let's start with case number 1. If Bob has 3 red connections, and we're a heartbeat away from concluding the proof, because if I have these 3 lines that you see on the screen, then what can I claim here? Help me out. I can consider these guys, A, B, and C, to which Bob is connected with 3 lines, right? And I can consider how are those guys connected. And now I have 2 possibilities. Then I have 2 possibilities. None, so 1, none of A, B, C connected. So no pair is connected there, connected. Then what do I conclude if none of them is connected? So they're all blue, right? They don't know each other. If that's the case, I just found the blue triangle. People agree?
Yes.
Okay. So blue triangle exists. Blue triangle exists. The only other possibility is, what is the only other? Help me out here. Either no connections, no pair of ABC connected, or what's the complement of that? Just logically.
ABC are connected.
Okay, that's why I was asking. Let's be a little bit more precise. That's
one of them is connected.
Yeah, at least one pair is connected, right?
Yeah.
So it could be, it's true, it's a possibility that all of them are connected. But another possibility is that at least one of the pairs, for example, let's suppose this pair is connected, A and B are connected. Okay, so the other possibility, at least one pair, okay, say AB, connected. If that's the case, connected, then we found red triangle. Do people agree? So either way, you either find a blue triangle or a red triangle, because from Bob, there are 3 red ones emanating. But now going back there, that was case 1. What if I have 3 blue ones? Help me conclude the proof. What if I had this situation here? I just carry out the same argument. Now I consider the blue connections from Bob and call these guys here A, B, C, or maybe X, Y, and Z, or whatever. And now I'm considering connections between X, Y, and Z. Either all connections are red, in which case I found the red triangle, or at least one connection is blue, in which case, let's say, I don't know, if this time like X and Z is blue, then here's a blue triangle. Either way, I find a triangle, either a blue one or a red one. Do people agree with me? Because I've just concluded the proof that was my proof. Okay, granted it's proof by cases. Okay, so kind of lawyer-like proof. But I wouldn't say it's an elegant proof, because so here's the assignment. Okay, first, do people have comments on this or questions or whatever?
I have
yes,
a question which may be annoying, and that is that could you identify a relation? So for what we just looked at is there are 6 people, so there are at least if you choose, there must be at least 3 that form this triangle relationship
of one of the colors.
Yeah, could you do that with other numbers of people? So could you say like could you expand upon that? Like,
well, why would this question be? First of all, that's what I was going to ask in a couple of minutes anyway, because that's exactly what's the most natural thing is. Okay, so let's actually do that now. Let me insert another picture. So what's the question that you just asked? I think where were we? Oh, we have.
I guess the question is, can you generalize the relationship between the group of people and the number of people who can be assured to be in this relationship?
Yes, and we'll do that right now. Okay, so the next question. So what have we answered now? Okay, so at first I was going to ask something else, but let's start with what you just suggested. So what we've shown that if we have and 6 people, then we have a guarantee for sure. Let me write it. So we have a guarantee then for sure, either 3 friends or 3 strangers. This is what I'm just simply rewriting what we found. Nothing new here, strangers. But I want to say the reason I rewrote this is, and I'm answering your question slowly, is that this number has a name. It's called Ramsey's number, sometimes denoted like R33, is 6, is the smallest number that guarantees or ensures 3 strangers or 3 friends. That's the definition of Ramsey number 33, R33. That's the definition. Strangers or 3 friends. Okay. Now I'm getting to your question finally. You're asking, what is the smallest number? That's one way. That's one thing you can ask. What is our, I don't know, 17? I don't know. Here looks like 12. 12-3, for example, or 12-31, or something like that. How about, let me ask you, what does this number stand for? How about R55? What have I just asked? In a way, I'm rephrasing what you've asked, right? Generalizing in some ways. So can somebody say in words?
The smallest number that ensures 5 strangers or 5 friends.
Exactly. Now, can I ask you the next question? What do you think this number is?
You can ask that, sure.
Yeah, I mean, I know that you may not know the answer, but I guess I'm asking, what do you think that number is? Just an estimate. What would you suggest? What does your intuition tell? I know that you don't know the answer.
Would it be 10?
Okay, 10 wants any other suggestions? Okay, 10, good guess.
I feel like it's greater than 10. I don't know why,
Okay,
but
okay. Some people feel it's not. Anyone else? Okay, so let me tell you the correct answer. The answer is we don't know. The stage of development of humanity as of today, our knowledge, is such that this answer does not exist. We do not know. And here's the feature of, but we have a pretty good estimate that it's between 43 and 49, if I'm not mistaken. They may have improved it slightly. But the answer is not known today. In fact, 49, let's say. Okay, so don't quote me on this. It may be 48 today, but yeah, no, we have a range, a pretty good estimate. But we don't know what this number is. And here, a couple of observations you can make. First of all, you should be stopping. Hold on, don't we live in the age of computing? I mean, we're making like easily, this laptop is making several billion computations every second, right? These numbers here that we're discussing today look tiny. And by the way, another feature is that the question itself, the way we've posed it in terms of the people and strangers and knowing each other, is understandable to a person at large, someone who doesn't have a mathematical background. This is what distinguishes this class from a class in calculus, where there to even begin the describe, yes, there will always be this need to describe the motion of the clouds, how they grow and how the waves move and so on and so forth. But you kind of have to have the knowledge of the language itself to begin looking at interesting questions. Here, we can understand we formulated a problem and we're already on the edges of what's known and maybe on the edges of what's knowable. May seem like a slight distinction, but another question you can legitimately ask, will we ever know what is our, I don't know, 7-7, for example? This, we might know someday, but, well, okay, so some people think we'll never know this, but I don't want to get into this discussion. But the point is that we don't know. We might know someday, unlikely, we might know. Okay, I don't know how much time we have, but okay, I'll tell you real quick. There's a famous mathematician, Erdős, who said that if an alien race descended one day and asked us to give R44, we should mobilize all the resources on planet Earth, all our computing power, and try to so these aliens come down and they tell you, you tell me what R44 is, or I will destroy your civilization, annihilate your race. Okay, so we could try to mobilize the resources if we cannot fight and give them the answer. Maybe one day we will. But if they ask for R55, posing the same conditions, then we should just fight back because we will never find it. Okay, but leaving that aside, and this gets into all sorts of interesting philosophical discussions too, for which we unfortunately will have no time because this is a different class. Final question. We have 2 minutes left. And now the questions that a couple of people already raised. So why not? Yeah, we do have computers. So what is it exactly now? And this is the question actually that you raised, even though it may not look like it's the same question. So what prevents me? I mean, 49 is a tiny number. Generating 49 objects on a modern computer or ancient computer for that matter is a trivial thing. It's 49 entities you can generate. You can draw connections between them, give the connection, assign to those connections like a color, blue or red or 1 or 0, whatever, and check. Do I have a triangle, or in this case, like a clique of 5? You can always check that, right? I'm checking for structures like this inside. Why this is not known? Why can we not check? So what's another solution? By the way, we gave a nice solution today. We have a nice proof. But along the way, a couple of you already suggested some other solutions. We talked about, someone mentioned the word exhaustive enumeration or something along those lines.
I'm still it's hard to believe that it's unknown, because like if you were to exhaust it, right? Like even computers, like if you ask the computer for a random digit, it's not really random. There's a formula to find that random number. So it's kind of like, how does it, like it would, like, so the random number in a computer, it's not random, it's an actual like defined thing. So it's like, how do we not have a defined thing using like defined objects? I don't know how was there a range of like not knowing if there's this many or this many connections if we plug in defined numbers? Like it's kind of hard to like believe.
Okay, so I'm agreeing with you that it's kind of hard to believe, although I'm not quite sure that I understood everything you said.
Gotcha.
But we can talk about this. Was there another comment before we talk about this?
So I think it's my guess is that it is likely an issue with the rate of growth of different combinations of like different diagrams, different like possible numbers and types of connections, even with something like 4 people.
Okay.
Because it's going to involve like on the order of factorial, if that makes sense.
Okay, so now so let's address let's make sense of them, because they both of these remarks make sense, but they may have been vague to many of us, including me. So let's try to make sense. Suppose I do have those 49 people. So what's a solution? What was it? Okay, so real quick, we have 2 minutes left. So with these 6 people, what's another way to solve this problem? Suppose I didn't feel like today, I don't feel like I wanted to like think logically for some reason. I'd rather play today, my piano. I don't want to engage in.
You could you could just simply attempt to illustrate every single possible way they can be connected.
Right. Color.
Yeah.
Right. So what I can do is I can take a graph on 6 people like this. Take all the possible edges, of which I know I have 15, right? Did I have 15? 6 years. 15 edges. How many different colorings are there of the edges? Notice what I'm asking now. You've already asked this question before, and I said I'll come back to it in like 15 minutes. And this has been more than 15 minutes, but we're back at it now. So I've drawn a graph with 15 connections. This graph, each of these connections can be either red or blue. Okay, each one. How many different such graphs are possible? Last question of the day, and we'll be done. And then
2 to the 15th.
Sorry?
Would it be 2 to the 15th?
Yeah, 2 to the 15th, right? That's nothing for the computer to do today. 2 to the 15 is not a big of a deal.
Yeah.
But now I'm asking, what if I had actually not 6 people, but there were questions were like 43, 49. What if I had like, I don't know, let's go with 50 people. Then what am I asking here? Just checking whether this is possible, whether I have a clique of 5 people inside the graph like this. How many possible colorings are there? Is it this many? Each edge, right? I have 2 to the 50, 2 to the 50 possibilities. Am I correct?
Yeah.
Just as you've suggested here. So because I have 50, oh, not 50 people. I'm sorry. If I had, okay. This is true if I had 50 edges. How many, if I had 50 people, suppose I'm checking something like this, about 50. How many edges would I have? 50 people. Then number of edges, all possible edges. We computed that number of edges.
1,225.
Okay, did you compute 50 times 40, 25 times 49?
No, I used the 50 choose 2.
Yeah, that's the same thing.
Yeah.
You did compute that. So that many edges, right? So like how much was it? About 1,000-ish, right?
1,225.
Okay, so let's say 1,000. So what am I computing then? 2 to the 1,000. Okay, what's our current estimate of the number of atoms in the observable universe? And compare this number to that. This is an unimaginably large number. The number of, so 10, okay, so if you want to be considered 10 to the 80, which one is larger? There's no way to check this. You will never have the computing power ever to be able to make that many calculations, even with the advent of quantum computing, whatever you want to hype these days. It's not going to happen, okay? So, okay, you need a little, so the point of today is, I guess you need a little bit more than simply brute force computation, and we'll return to this thing later. Okay, so that's one of the places where actually mathematics is useful.
And even the 2 to the 15th, to give an exhaustive proof would require drawing like over 30,000 different diagrams.
Yeah, exactly. But that's manageable for a computer, right?
Sure.
Today. This is never manageable, and this is manageable today, but that's another proof. So you all had this suggestion, and I didn't pursue it like, I don't know, half an hour ago when you suggested, but this is another way to prove it. Actually, later in the course, we'll see a theorem that kind of even to this day defies some nice mathematical proof, but is solved on a computer. We'll see, when we talk about planar graph and graph coloring, we'll see that. So we'll talk about graph coloring later in another context, and something similar, not quite related to this, will come up. Okay, so we're done for the day. Now we're a little bit over time. So you know what the assignment will be. It's not posted yet. Number 1 assignment is be respectful to yourself. By this, I mean, write up your solution neatly. What this means, that please don't wait to the last day, right? Write up the solution now, put it aside. In 2 days, you'll forget what you thought, okay? Return to your own writing and see if it makes sense to you. Please note, what I'm saying is that you're always writing for yourself. That's why I mentioned something along the lines of self-respect that may sound lofty or irrelevant or stupid to you, but it makes sense. Write it for yourself so that when you come back to it, you don't generate within yourself this sense of annoyance at trying to understand something, as you will undoubtedly, by the way, have when you will be reading the textbook at some times. So you have to work with that emotion too, right? So please write it neatly. And eventually submit your clean write-up of this. Your write-up will reiterating what we've already discussed. So right now you may feel like you understand it. If you do feel that way, it may be true, or when you sit and write it down, you may discover it was false, but then you write down the solution anyway. Or you may feel that you don't understand it. Then when you come down to write down the solution, maybe you'll understand it then. Okay, so the point is, at the end of the day, you want the solution written solution, nicely written solution. You will upload that, and then I will ask you a couple of questions about it. Okay, and that will be your 0th homework, homework number 1.
When is this homework due, by the way? Sorry.
This homework does not have a due date, and the reason it does not yet, it will be due by the end of this week. So sometime I may make it like mid of next week, and the reason this first homework is kind of not set in stone. Every other homework due date will be set in stone. We may adjust some as need. Well, be because we have a holiday next Monday, right? So we're missing one class. We have a class on Friday, which I'll see you then. I'm about to say goodbye. I'll see you on Friday, but then we'll have no class on Monday. So please start working on it now, right? I'll post it tomorrow on Canvas, and you will see the due dates and everything else will be on Canvas. Okay, make sense?
Sounds good. Thank you.
Okay, so you'll see them.
Professor?
Yes.
I want to know, like, is the class online or like in class?
The first few lectures will be online. So right now you have the Zoom links to about 5 lectures. We'll only need 4. You have more links there than we'll need. On the 24th, I hope to see you in class. That's I'm looking forward to seeing you in person so that we have this discussion on the board. We're not going to be using slides anymore. We'll be drawing on the board and we'll be discovering things there together. Right?
All right. Thank you.
No, so please note, I'm not here to preach. We want to come and have a conversation and solve some problems in class. Okay. The point is that you grow. Okay. I'm just another guy to guide you like that in the classroom. That's my role. If you want to watch some guy on TV that knows some stuff, then there's always YouTube, right? There's a lot of information there. In some sense, you don't even need to attend the university to get a Nobel Prize, right? All the information you need to get the next Nobel Prize is really there on the internet, but nobody has ever gotten the Nobel Prize without attending a university and coming to classes like this, and a bunch of them, and talking to others, right? Anyway.
Did you say that we have to come to the recitation on Wednesday?
Yeah, there will be a recitation because you'll meet your recitation instructor, right?
Mm-hmm. Okay.
And it will not be a long recitation because this time you don't have a quiz this week, right? Mm-hmm. So I'm not going to give you a quiz now about this, like in 2 days, right? So you normally have a week to have these ideas swirl in your mind a little bit. I suppose people call it marinate, let the ideas marinate. But you'll have a week to work on the homework before you get a quiz like on that.
Thank you.
Yeah, will the recitation also be put off until after the 24th?
No, the recitation will be this week. It's just this week's recitation will be brief. You'll have recitation on Wednesday. Does that
will it be in class or all virtual?
Oh yeah. So it will be virtual.
Okay, okay.
Okay, so your TA will post the link to the recitation, just as you have the lecture links that I posted there. Mm-hmm. Your TA will post links to the just 2 recitations, and then we'll do it in the classroom. So you'll see the link on Canvas.
Super. Okay, thank you.
Right. Okay. All right. Any other remarks?
Will you be taking attendance with Zoom?
Yeah, we'll be taking attendance, but well, not today, right? So maybe like the first week, no, right? Because some people will take a good look at me and they decide that this is the guy, he bites, I don't want to sit in his class, and will run away, right? It happens. Other people will join in, right? So we have this drop and join period for now. So the first couple of lectures, but I think next month, Friday, I'll start taking attendance. Yes, so the short answer is, yeah, we'll be taking attendance. Anyone else? Okay,